Okay, hello everyone. Welcome to the neurocomputing lecture. Can you hear me?
Yes.
Right.
Yes.
Yep. All right. Thank you very much for that. So don't forget to take your attendance. Yeah. Don't forget to take your attendance on by scanning the QR code on Spectrum. So this week's lecture will be using the same slides as last week, right? This week lecture will be using the same slides as last week, which is this 5 and 6 backpropagation 2, automatic differentiation. Last week we've done the forward pass, right, or forward automatic differentiation. So this week we'll be doing the reverse or the reverse AD, reverse automatic differentiation. Now, just a moment, yeah. Pull this here. Just see. Sorry, excuse me.
Doctor, are you speaking right now?
Thank you for that. I forgot to unmute my mic. Thank you for that. So just to recap what we've done last week, right? Last week we did the automatic differentiation, the forward pass or the forward AD, right? Given the problem of x equals something, y equals something, where x and y are functions of some variable t, and b equals sine of x, a equals ax times y, c equals a plus b. We have built the computational graph, and we've seen that when we have built the computational graph, as we are building it, we can also compute the local gradient, right? dA of dz and dz dB of dt and so forth, right? So, and now by using the chain rule, right, we are uh, you know formalizing how we want to represent this in our automatic differentiation problem, right? So we can use chain rule here, right, to compute dz of dt with respect to t, right? Because we know we have computed the local gradient before that, right? So, and we've done the lab as well, or the tutorial for the forward AD, where we have used the concept of dual numbers, right? If you remember. So we have used the concept of dual number, right? Where we have stored the values and the gradients, and we have seen that by using the dual number, we have seen that if we seed one of the variables with 1 and the others with 0, then we can get the partial derivative of z with respect to x. And if we do it the other way, we receive x equals 0 and dx equals 0 and dy equals 1, then we can get the partial derivative of c with respect to y. So the problem is, if we have many variables, then we need to run the same program all over again, right? If we have 1,000 variables, then we have to set 1,000 times and run the same program, which is computationally inefficient, right? So that's what we've done so far. Now, in the reverse mode AD, or reverse mode auto differentiation, right? Since the chain rule is symmetric, we can flip the denominator and numerator, right? Here, to dz with respect to ds, so partial derivative of z with respect to s can be flipped over, and you can do the partial derivative of s with respect to z using the same chain rule. Okay, so if we just I'll just use this. Right. Right. So previously we have f of x, y, right? Maybe not f of x, where x is a function of t, right? Can do this, then if we can do this, then we can flip it over. So this will be dx of df times dt of dx, right? So in this way, as in the first chain rule, right? As if you're canceling these terms, right? But of course, we are not canceling those terms, right? As I said before, these are partial derivatives and they are not fractions. But in the second chain rule, when we flip it over, it's as if we're canceling the other way around, right? As if we're canceling the other way around, because we have flipped the variables over. So in this first case, we are taking the partial derivatives of f with respect to t, and in the second case, we are taking the partial derivatives of t with respect to f. So this is the symmetricness of chain rule. We can do this. We can use this. Right? Now, so for the previous problem, if we apply the chain rule, right, we have some variable s over here, right? So why s? Because the previous forward automatic differentiation we use t, right? So for the reverse we'll use s. It should be the other way around, I guess, s and t instead of t and s. Anyway, so the idea is because we want to set ds of dz equals to 1 at the end of the day, right? So at the end of the day, we want to do that. So we have this problem. And then if you apply the chain rule, right, I'll show you in a moment. Yeah? I'll show you later. Then we have to reverse our way of thinking. It's because in the forward mode, we know that variable A is dependent on X and Y. Variable B is dependent on X. Variable Z is dependent on A and B. But in reverse mode, we need to reverse our understanding. So X affects A and B, Y affects A affects Z, and B affects Z. I'll draw the computation graph afterwards and kind of demonstrate you the whole kind of a big picture of it. Okay. Now, how do we implement this in code, right? So I'll just skip a few parts because I'll be showing the details later. But to show you that if we substitute s with z, right, then we can get the partial derivatives of dz with respect to x, and the partial derivative z with respect to x, and the partial derivative z with respect to y automatically. So once, it doesn't matter how many variables you have or how many input variables that you have, you only need to see the last or the end of the variable as 1, or the partial derivatives of z or s with respect to z as 1, and then you can calculate for the whole partial derivative with respect to the variable of inputs. Now, hence, we no longer need to run the program 1,000 times, or in this case twice, because we only have 2 inputs, x and y. So this is reverse automatic differentiation. And later we'll we'll talk about the expression graph, and later we'll see how the reverse mode automatic differentiation is implemented, right? It's actually implemented. We are using previously in forward AD, we are using the class of dual numbers, but here we are defining another class called VAR or var or variables, I guess. Yeah. So, and in this class, we are storing the children's, okay, the children. So we have parents here. We'll be storing the children. We'll be talking. I'm just going through briefly before we go into details. Yeah, before we go into details, we'll just go through the slides briefly, and we'll see how we can in this class of var, we have to define the differentiation rules, right? We also have to define the differentiation rules as we have done in the forward AD computation. But of course, how we defined it in here, what makes a difference, from the forward AD is that we have to add the variables as children's to which variables. So we have to make that link, right? We have to make that link. So there's a list here. There's a list self.children. There's a list here which stores the children's of that particular variable. Okay. So if x has children a and b, x will store a and b as well, right? Or the local gradients of a and b. We'll see that afterwards. And so that's about it. Okay, that's about it. I have some announcement, which is my slides are only up to today. After this, we will not be using much of the slides. Okay, I don't have any more slides. After this, we'll be using Sebastian's slides, maybe a little bit, but mainly will be I'm hoping that we will be using the collab mostly, right? Most of the lectures will be done in collab, so no more slides, right? So that is the overall view. Now we'll go in detail for the reverse mode auto differentiation. Before I proceed, do you have any questions? I've just talked about, if you don't understand, right, up until now, this is okay, because I'm just talking about the overall idea or the overall view of what we're going to do today. So if there are no questions, I'll just proceed. Yeah? So back to the forward and reverse AD. So we'll do the forward. Yeah. So we have the forward pass. Right. So you have the problem of x equals something, y equals something, a equals x times y, b is the sine of x, and z is equals a plus b. Right. Now we've done this forward computation. Right. At the same time, we can also compute dA of dx, which is y, right? So how you solve for this, we've done previously, lah. So please refer to the previous lecture. And dA of dy, which is x, and you have the dB of dx, which is cosine. Let me just rewrite this. Right? A equals x times y, and b equals sine of x, and z equals a plus b, right? And then you try to compute the local gradient. Right? So the a of dx equals y, and the a of dy equals x, and dB of dx equals cosine of x, and dB of dy equals 0, dz with respect to a equals 1, and dz with respect to b equals 1 as well. So if we compute, if we draw the computational graph again, so this is just a, what we did last week, right? So x and y over here. So x goes to sine of x. So we have b equals sine of x. And then you have multiplication over here. And you go over here, so you have a equals x times y. And then you combine both of them. Right? To the variable z over here, which is z equals a plus b. Right? Now, I'm going to write in blue. Should write this in blue as well. But, we get the idea. These are the local gradients. Just write this in blue. dz over dA, right? So what do we have here? We have dB over the partial derivatives of B with respect to x over here, right? Which is I'll just that away. Which is cosine of x, right? And I have the partial derivatives of A with respect to x, which is y. And here we have the partial derivatives of A with respect to y, which is x. Here we have the partial derivatives of z with respect to A, which is 1. And then we have the partial derivatives of c with respect to B, which is 1 as well. Okay. Did I miss anything? No. I think that's it. Yeah. Now we are going to assume a variable s. Right? We're going to assume a variable s. Right? And we are assuming that because we have variable s, we have ds of respect to c. Right? So here we'll be computing our backward pass. I'm going to do it in red. Right. So we have in our backward pass, we have ds dz, which we don't know yet, right? We haven't set it. And then we can, using the chain rule, we can do this, right? The partial derivative of s with respect to b, which is because of the symmetricness of the chain rule, right? So anything in blue is a local gradient, yeah? We've computed this before, here. Yeah, just be careful. So that's why I'm writing in blue, to make it very, very explicit. Okay. And then we have do we have space here? Yeah, I'll do. No, I do one right there. So I'll write here ds of with respect to A. So the partial derivative of s with respect to z times again partial derivative of c with respect to A, which is this guy. Which is this guy. And we can continue this, right? ds of dy. This is going to be a bit long. Maybe I don't write it here. Well, make it nicer by doing this, and I'll do this. Yeah. Maybe I won't write it here as well because we don't have space. We don't have space, yeah. So I'll just write it here. ds the partial derivative for s with respect to A is equals to the partial derivative for s with respect to z times the local gradient, which is the partial derivative of z with respect to A, right? And then we can go on some more. So the partial derivative of s with respect to y is equal to partial derivative of s with respect to A, which is this guy, right? Times the partial derivatives of A with respect to y, which is this guy. And then you have to add, right? Remember, because this is a chain rule applied to multivariables, right? Chain rule applied to multivariables, you have to add, right? And the partial derivative of S with respect to B, which is this, right? Times the partial derivative of B with respect to Y, which is of course this one, right? Just write it everything out explicitly, right? And then of course the last one you'll do the ds of dx, which is the same, right? Same shape, yeah, not the same lah. The equation is different, but the shape is the same. The way, the method is the same. I'll just write it down here. Plus ds with respect to dp times dp with respect to dy. Oh, maybe I want to space that. So I'll just write it again here. ds over dA plus ds over dp. And then here I'll just populate the dA of dx plus dB of dx. Yeah. Now, if we do S is equals to Z, we substitute this. So ds of dz is equals to the partial derivative of z with respect to itself, which is equals to 1, right? So what we're going to do here, we're going to seed this as 1. What happens? We'll do it as 1 here. Then I'll just label here. The SDA, SDP, and we have ZY here, and also maybe of dx over here. Yeah, I'll just label this first, so you can see. You can see the whole process. What's going on? What's going to happen? Yeah. So here, we are substituting the variable s equals to z. So any partial derivatives or any derivatives of a function with respect to the function itself is equals to 1. And then if you seed that, right, it's the same as we've done the forward lah. But this way we are doing it from the other side, right? We are doing it from the other side. So if we seed 1, what happens here is, because this will be 1 times, I'm just going to change color here, right? Where does this 1 comes from? Obviously, this comes up here, yeah? Comes up here. So anything that is in red is a backward pass. Anything that is in blue is the forward pass. So again, we are just seeding this, right? 1, ds of this respect to z is equals to 1. dz with respect to a is equals to 1 because of this guy, yeah? We already computed that local gradient, right? What happens for the partial derivative of s with respect to y here? We'll take the partial derivative of s with respect to a, which is this is 1, right? 1 here, 1 here, 1 here. So this is 1 times dA with respect to y, which is x, right? So 1 times x plus ds, the partial derivative of s with respect to b, which is this one. So conveniently, we have, for ds of dA and ds of dv equals 1, but for maybe you have different values if you have when you have different when your equation is different, yeah? When your equation is different. 1 times dB, the partial derivative of b with respect to y, which is 0, right? So that is very convenient. No, I have to do it in blue, right? Because this is a local gradient, right? So, and here you'll have x. And so you solve for every part of the equation, right? I'll just go on. By this point, at this point, you probably have figured it out, right? E of dx is y plus ds of db equals 1 again, because of this guy, yeah, plus 1 times, and db of dx, so the partial derivative of b with respect to x, which is this guy, cosine of x, which is y plus cosine of x. So these are your backward pass, right? And if we fill it up, right, ds of db equals to 1. The partial derivative of s with respect to a, or this is also the same as like this lah, right? But I don't want to write dz with respect to dA, because I don't want you to confuse with the forward pass, right? I don't want you to confuse with the forward pass. Now the forward pass, the local gradient, right, now is taking the gradients from this side of the network, or this side of the computational graph, right? In our case, it's computational graph. Here it'll become 1. It becomes 1, right? Because we are substituting s equals to z, right? So this becomes, it's actually effectively dz, or the partial derivative of z with respect to b, right? But I don't want to write that, because then you'll be confused with the forward pass, right? But this is a big assumption that we are making here. We make a very big assumption here. Okay. And what do we have here? We have x over here, right? Because of this guy. And we have y plus cosine of x, right? So you can compute just by seeding 1 at the end of the computation graph. You can compute both of these partial derivatives automatically. So even if you have 1000 input variables, just by changing this into 1, or by allowing gradient to flow in, right, you can, and you reutilizing the local gradient, or the catch local gradient, you can automatically compute the partial derivatives of the output function with respect to the input variable. So what we want to do is, of course, at the end of the day, in our neural network, we have errors here, remember? I just, yeah. And we have weights here. Of course, we have inputs, but we also have weights, weight 1, weight x, and weight y, right? Because the inputs are x and y. At the end of the day, we want to calculate the partial derivatives of errors with respect to weight x, and the partial derivatives of errors with respect to weight, just do this, weight y, right? Why do we want to compute this? Because we want to update our weights, right? Using the gradient descent, right? We want to do wx equals wx minus alpha t over this. We want to do this. We want to update our gradient, our weights, sorry, by using the gradient and going down the gradient descent. Where we are using the gradient to go down the gradient, right? So we're descending the gradient. So this is the whole picture, the whole picture. So I'm just going to pause for a while. Are there any questions? I hope this is I tried to make it as clear as I can, right? So if you have any questions, please ask.
Doctor, I have one question.
Yeah.
For the dsdy, uh, equals to the SDA over the ADY. Why we plus it with the SDB?
Because you have for this is the just a moment, yeah. Because the chain rule applied to multi variables. Yeah, just bring this again. Bring this up again. So if you go Wikipedia chain rule, right? So you have multi-variable case, right? So I'll explain it in simpler words, in simpler terms, lah. Because it's this can be kind of confusing. But basically, revisiting chain rule, right? So revisit chain rule, right? If you have like x is a function of t lah, right? So and then f is a function of x, right? So it looks like this, right? T, and then you have some x as a function of t over here, and that is channeled into or funneled into the function of f, right? And then you have f of x here, which is some equation, right? I don't know. You want to find the partial derivatives of f with respect to t, right? You're not trying to find the partial derivative of f with respect to x. You're trying to find the partial derivative of f with respect to t. Then you do this. This is by the chain rule, right? As if you're cancelling this term, but of course we are not doing that because of the these are not fractions again. So this chain rule for one variables, yeah. But then if you have multivariable calculus, right? Or multivariables for chain rules, yeah? Multivariables rules for chain rules. So if you're in the case for multivariables, right? I just draw this here. Right. So here, if you kind of draw the computational graph, I'll just do box here, yeah, because it's a function of x, right? Right, and then you have the output, right? So for multivariables, right? Consider 2, right? You have x, which is a function of t, and then you have y, which is also a function of t. Yeah? The rules is that they are both must be the function of the same variable, right? It must be the function of the same variable. If x is, for example, a function of t, y is a function of, I don't know, u, then it doesn't work. Okay? Have to the function of x and y must be dependent on the same variable. And then you have f, which takes the function of x and y. Of course, we don't know what this equation is. And then if you apply the chain rule, then you have to consider both cases, right? So df of dx, no, dx, not dx, dt, dx of dt plus dy of dt, right? This is if you have t, right, and it goes over here, x of t, and it goes over here, y of t. and then it comes again over here, which is f of x and y, and then you have this. And of course, you can generalize this multivariables. What if you have lots of I'll just do x1, x2 lah. Okay? x1 equals x1t, x2 equals x2t, blah 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 blah. So you have like maybe 1,000 or 10,000 xi. I don't know, right? So xn of t, and you have a function of f which takes all of the input variables x1, x2, blah 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 blah, xn, right? Then the chain rule also applies in this manner. So you have to sum dt, which is the f of the x1, dx1 over dt, plus the f of the x2, dx2 of dt, plus blah 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 blah, plus f with respect to xn times dxn over, right? So if we are you have like a t here, but you have x1 up until xn, right? And those variables then becomes the input of f. That's why in the slides it's written in the summation form, right? So I'll just borrow this space lah, right? So you have what is it again? So df of the partial derivatives of f with respect to t is equals to the summation of I equals 1 until n, summation of x xi over dt. Yeah. So this is the summation form of it. Yeah. Rather than writing it all out. Yeah. So hopefully that helps.
Doctor, can you go back to the other back to 5. Slide to slide 2.
This one.
Yes. Because for the we calculate for the ds over dy, right? But
Dx,
the problem is
dy.
ds over dy for yang you dah write yang you dah tulis belah kanan tu, ds over dy. Okay, equals to ds over dA over dy. Why we will want to find the ds over dB since d is the function of x, right? It's not the function of y also because it's only the function of x, right?
Sorry again. So so we have this equation.
Okay. You want to find the what do we call
Partial derivatives.
partial derivative of itulah ds over dy tu. Okay. Then ds over dy equals to ds over dA since the a is a function of x and y, right? But why do we put the ds over dB since dB only the function of x only kan?
It's just for formulation. Just for formulation. Because dB, ds is a function of b lah kan. S is as you can see. If you think of s as z, right? So z equals to a plus b, right? Right. So it is a function of b in a way for this guy, right? But b itself is a dependent on only x, yeah. So we have this part. So we need to find it in formalizing it, right? We need to consider this, right? But in effectiveness, because of our equation is given by this, then this is 1 times 0 lah, right? Because we have 0 over here, right? So it becomes 0 because it is not B is only a function of X, not a function of Y. But if you think, right, in generalize, we are thinking in general, in more general terms, if this, for example, right, sine of X plus 2Y, for example, yeah, then this term on your right over here, this second term on the right hand side, will be alive, right? Will be effective, will be active. Yeah, so this is 0 lah because doesn't exist, right? We just set it to 0.
Thank you, Doktor. Dah
Okay.
faham dah.
Right, sure. All right then. So hopefully these kinds of, you can see how the forward pass and the reverse pass. Before this, we are doing. I'll do the blue for the forward. Yeah, we'll be doing for the blue for the forward, right? And then we'll have the red for the backward pass, right? We have to wait for the backward pass, and it reaches this guy, right? Reaches this guy. So as you can see, by doing the forward and reverse automatic differentiation, or the reverse automatic differentiation, we only need to see it once, right? And then it calculates the partial derivatives of the output with respect to the input for all of the input variables. So how should I say this? The takeaway, I guess, from this reverse automatic differentiation is that it's simple, but it's quite clever. This is what I said to last year's batch as well. This concept is simple, but it's actually really quite clever, because if you consider, if you have like 10,000 variables, if you have maybe 1 million variables, and of course if you are using deep learning, you can have many input variables, right? So you can have I don't know how many features you have, right? Maybe 10, 20,000 features, I don't know, right? So in those cases, this really helps. Or else you have to make 20,000 calculations every single iteration, which is going to make your algorithm very slow. Okay. All right then. Hopefully that's you understand that. Okay, so now, if you have no other questions, then we'll be looking at the implementation, right? Of course, I have some codes over here. Before we go there, we'll have a look at the slides again. All right. So we need to talk about the expression graph, right? So how do we actually implement this, right? So we've done this doodling on Jamboard on the computation graph and how forward and reverse automatic differentiation works. But how do we translate this into coding and into programming? So we are using the expression graph. We think about it, right? The goal is to get something similar to the dependency graph below, right? Now, what is the difference between this graph and the graph that I've just drawn just now, right? So how different is this graph from the graph in the slides, right? Now,
this one doesn't have any directions.
That's correct. And also, this one's, of course, is the most obvious difference. You would say to me that, hey, doctor, is actually in your graph is kind of a sideways, right? So this is more like a neural network convention way of drawing graphs, right? or if you're drawing the graphs or no, you're drawing this way. But in this way, you're making like a classic graph entry, like a classic graph entry, right? So you have the input variables on top. So there's a reason for that, because we want to think X as parents. So X, the input variables are parents, right? So Y is also parent. So X has two child, which is B and A. So whatever X does affects B and A. And Y has one child, which is A, right? But B and A, both B and A has one child, which is Z. So you have to think as X as a parent. So this is why is the graph is drawn like this instead of rotating it in 90 degrees, right? So the roots of the graphs are the independent variables X and Y, right? And then, so by doing this, now what we want to do is we want to store the relation, right? What the information? Who are the children of X? So B and A belongs to X, right? B and A belongs to X, and A belongs to Y. Z belongs to B and E. And how do we do that? Is by using we are defining a new class called var or variable, right? So in this class, whenever you initiate it or instantiate this X equals var or something, right? You're assigning its value, and also you're assigning its children. Okay? So for example, X equals var 0.5, right? Afterwards, right, when we do the calculations for A, which is this, right? When we define A, we'll store the information of A in X. We'll see this. Yeah, we'll see this later. So okay. So here, what does each var node store? Each node can have several childrens, right? In the example, X has both A and B as its children. Cycles are not allowed, of course, in this graph. And fortunately, in neural networks, well, aside for recurrent, right? Well, can we do that? Can we see? Yeah, in most, for example, multi-layer perceptrons, right? The cycles are the network has no cycles, right? It is you start from the left side and you proceed to the right side, right? From the input to the output. Okay, so the roots of the graphs are independent variables X and Y. So if you create a node, for example, like this, X equals var 0.5, you see and you haven't assigned A or B or anything or Z, right? Then by default, the list of children will be empty, right? There will be no children here. There will be no children here. And then how do we store a child, right? So we have this multiplication here. So whenever a new expression is built out of existing nodes, right? The new expression registers itself as a child. It will also save its contributing weight, right? And this weight will be used later to compute the gradients, right? So this weight will be used to compute the gradients later. Right. So here we are again defining the multiplication operation or overriding the methods, right? So here is C equals X times Y, right? Or A equals X times Y, right? And then what happens to the weights, right? You have to append the values into the list of your parents, right? Because you're taking self and others here, X and Y. I'll show you in the codes later. And then once you have done storing the child, you also have to calculate the gradient. So you have self dot value here. Now, when you're doing deep learning with Pytorch or with TensorFlow or with Keras or anything, you won't see this. You won't see this part, or automatic differentiation, or how the gradients are stored, right? But these are, you know, if you're trying to if you have a need to kind of tweak this part, so this information or this knowledge will come in handy. Okay. So in here, we're propagating the derivatives, right? So we are calculating the derivatives using the chain rule. The chain rule is applied here, right? So the local gradient will be catch as we go forward. I'll show you in the codes in a while. Yeah. I think because if you look at the slides here, it doesn't make any sense. You have to look at the codes in the whole code. You'll have to see the whole code for you to understand this. Yeah, this moment. Yeah. Okay. So I've uploaded the code on GitHub, right? So the next 40-50 minutes, there is a question. There's a exercise that I like you to do. So please have a go, right? Maybe you say, Doctor, I don't understand the codes, right? Have a look at the codes first. Have a look at the codes first. And how, because if you look at the codes, you study the codes, right? You'll see this is the self.children is where you store your children, right? This is where you apply the chain rule. And this is how you define or formalize the differentiation rules, like we did in forward automatic differentiation. Okay. So basically, what this does, right? I'll just give some more explanation over here, I guess. Because this part is maybe kind of confusing. X equals y, self, y equals other, if z equals x, y, then dz of with respect to dx is y, right? And dz, the partial derivative of z with respect to y will result in x equals to x. What happens here is it is append equals y and z values, which is calculated over here. This is just z equals, that's all, right? Where x is self, y is other. Okay. Here, x has to be of y. So have a go, right? You need to complete the addition to division, subtraction, and the power function, right? how would you do this? And of course, the sine function is given here, right? So you add other functions as well, your addition, your subtraction power, and through division. And maybe you want to have a test, right? If you test it correctly, this will not have any errors lah. And then we'll do the forward computation. And see how once we've defined the operations or the methods here, right? We can do the forward computation, and then we'll see the values of C, right? Please ignore that we have two C values, right? Maybe just one. And then we'll see that by seeding these values, you automatically calculates for the partial derivative of Z with respect to X and Y. Okay, so have a go at this first. I'll give you about maybe 40 minutes. Yeah, and then we'll come back in 40 minutes and discuss it. C, right? Just one. And then we'll see that by seeding these values, you automatically calculates for the yeah, and then So hello. So we're back again. We have 10 minutes left. How are you guys doing?
Good.
Yes, doctor. Okay.
Managed to you managed to code, yeah, the methods, the overriding methods, and this has no errors, right? Then when you do the forward computation and see how you'll see how the children's of the variables are stored and so forth, yeah, right, so forth. And then for the reverse mode computation, if you have no errors, right, if your code is working perfect or okay, right, then this will be okay lah. There will be no errors lah. The values you should get about should be around this one, right? And the difference should be less or equals to very very small error, right? So do you have any questions? Any questions so far? I think it should be hopefully it is quite clear because I've tried to make it as explicit as I can, and hopefully what my hope is that you can appreciate how very simple the concepts are and yet how clever it is. How it's a very simple concept, not very complex computation or something, but the concepts are very simple, but it's quite clever. Yeah, that is a thing that I hope you can appreciate. So you have, and I think because I have to go a little bit early today, right? So well, not really early. By our usual standards, it's a bit early, lah, right? So we'll probably discuss this. We'll discuss this in our tutorial next week on Monday. Give some time for those who haven't finished yet, right? Not sure. Maybe all of you have finished. I don't know, right? So, and then we'll have a look at how the children's are stored, what are the gradients are, and what when you see the values, what happens to the gradient or the local gradients, or the computed the backward pass, right? The local gradients are there, right? You have when you do the forward computation, you also compute the local gradients in a way. But then when you see it, what happens to the gradient itself, yeah, for every variable. To talk about that in the tutorial, and I think in the tutorial I'm targeting, if we can, we'll try to do an introduction to Pytorch, right? If we have time, right? If not, I'll bring it over to the lecture, right? So as I mentioned earlier, this is the last time you'll see the slides of my slides, lah, right? You won't see any other slides from me personally. So I'll probably use some slides from Sebastian's, Reshka, or some other materials, some other sources, right? But these are the limitations of my slides. From here onwards, we'll be doing, we'll be more doing Pytorch, yeah? Because slides, slides and theoreticals are boring, right? So you want to try to implement and practice what you've learned, or practice as you go along, as you learn along, right? So you want to do that. So just by saying, so we can say goodbye to the slides for now. We are not going to use, we are not going to code everything from zero, right? For Pytorch automatic differentiation, we're going to use the library, right? Like I said, the Pytorch, pretty much of everything today is, automated, right? We have some built-in functions for them, right? You can pull from different libraries, things like that. So Pytorch automatic differentiation, again, it builds computation graph as it runs. So you don't have to build first and then, and do the calculations. It builds as it runs, and it catches the gradient in the same way, right? It has a clever memory management, right? And Pytorch is the backend is actually written in C++, and so it's fast and can be multi-threaded. Yeah. So that is all for today. I will talk about the answers for the reverse AD in the tutorial, right? So if you have any questions, please ask me. If you have any questions regarding the assignments, you can ask me as well. Yeah. And don't forget that 26th of April is the deadline for assignment. Yeah. Don't forget that the deadline is next Tuesday, 2 p.m. And please submit your Google Colab link. If you've done your work on the local Jupyter notebook, that's fine. As you need to upload it in the Google link so that I can just, it's easy for me to mark and grade your coursework or assignment. Okay.
But I can ask a question regarding the assignment.
Yeah, sure.
And since you mentioned that we have to create our own basic data set, how do we assure that the data set is linearly separable?
You can, for example, right? For example, you want your new data set to not be too far from your training data set. That's one way. You can, for example, take your training data set, add some noise, add some random noise. And of course, the random noise is, some Gaussian random noise or something. But as long as your noise is not too big, right? The standard deviation of the noise is not too big, then you should be able to, get a test data set which is similar to your training data set.
But aren't we also creating the training data set as well?
Yes. I know. I understand that. The one way I've done this is something that you kind of how should I say, tune it yourself, right? You don't want the nor as long as the nor and the yes classes are not too far apart, right? And you only have two classes, right? So they are in a way, because we only have two variables, x1 and x2, Mary and John, right? So it is easy to visualize, right? So as long as it seems that you can draw a line, then you'll be fine. It's linear separable.
Understood.
Right? If your data set, kinds of like looks like a U or some S or quadratic or cubic, then then it's a problem lah. But if the decision lines, it looks like you can draw a line, then it's fine.
Understood. And just to clarify any sort of doubts that I have, when I have the two labels, basically for X1 and X2, which is basically John and Mary, I just want to fit the perceptron in a way that I find a linear classification line or a decision boundary between the two, right?
Mm-hmm. Yeah.
So just create a data set, fit a decision boundary between Mary and John, and that is it, correct?
Yeah. That's it.
Understood.
Okay, and the one of the other points that I'm want you to have a look is you're doing the different versions of stochastic gradient descent, or
yes,
the different versions of gradient descent. So one, you have the compulsory stochastic gradient descent, the SGD, and the other one is you have to choose whether you want to use the batch or the mini batch. And I just want you to appreciate what are the differences are, and see how the difference in the variation affects the performance of your training.
Understood, Doctor.
Okay.
Thank you so much.
Sure.
Wish you nice.
Okay. So we have no questions. That's all for today, yeah?
Sorry, Doctor, just a quick question. Can I just create a complete data set and split it in a 7:3 ratio, and 7 to be the training set and 3 to be the test set?
Sure. Can. You can maybe 1,000 or 500. As long as you generate the data set yourself lah. Right. You generate it yourself, and then you just split it. That'll be fine.
All right. Thank you, Doctor.
Sure. So you have no other questions. That's all for today, and see you next Monday.
Thank you, Doctor.
Welcome.
Thank you so much, Doctor.
Thank you, Doctor.
Selamat